Hi. This second half of Chapter 6 starts off with building a universal shift register. So it's showing you the first application of flip-flops, but there's a bunch of sub-goals here. One is to see how you chop a large problem up into small problems and see how the adding of remembering or memory increases the functionality of the circuit. But the bigger goals are to sense something really significant changing in our circuits. It's the difference between a chair and a car in mechanical engineering. A chair, yeah, as human beings we can pick it up and move it, but once we're done it just sits there. It doesn't roll down a hill, we can't put a motor in it, that kind of a thing. This is that big change between writing a program that just executes one line at a time without any loops. Here we're adding loops. So I've given you two analogies. We start off with a homework problem from Chapter 5 on the shift register. I shot a video of it, and there's a circuit and logicism associated with it. So we're going to compare this flip-flop circuit with the Chapter 5 circuit. So here we have a circuit that on the clock pulse everything shifts right. So what is the difference between this one and the Chapter 5 circuit? Here the inputs are coming in serially, one at a time, up here on this pin D. The Chapter 5 homework problem, Chapter 5 had parallel output and parallel input. Well, here we can see it doing parallel output. We just pull the contents of the flip-flops out. And here we can see it loading data in parallelly, so that's parallel input. Now if you remember, the Chapter 5 circuit could shift right once, shift right twice, or shift left. And shift left just once. Here, our circuit can shift right 3 times, 4 times, 5 times, 6 times. Left 1 time, 2 times, 3 times, 4 times, 5 times. And here's the final circuit and logicism. Now, if you load this logicism file in and start playing with all the sub-circuits and see how I've designed it, you can see how I've chopped it up into smaller pieces. This is the first piece right here. I just used the mux, straight out of logicism. And this circuit right here becomes these 4. So this circuit's duplicated 4 times. We call these modules. So this circuit right here, it turns into 4 modules. And then I attach to the 4 modules for the D flip-flops. And then I organize this circuit so I can package it like this. Play with that logicism file and see how I have it organized. This is a field programmable gate array, and we're programming it with the virtual hardware definition language. The stuff in purple here is part of that language. If we had other lines like this, they'd all be operating in parallel, not sequential like a programming language. What causes these to be executed in sequence is this process. This process creates flip-flops. So this if structure right here creates the flip-flops that we're talking about. So what we're doing is we're seeing the evolution of the if command, or the while, when, the for, next, if, case, whatever looping construct that you've ever stumbled across in a programming language. What you can see is the sequential programming language evolving into the looping constructs here. The looping constructs have memory. Now, moving from stuff that's stationary in Chapter 5, like a chair, to something that moves on its own, that has independence from us as a human being. We can let it go. We can let the car go and roll down the hill. We can attach a clock to this circuit, start clocking, and it'll sit there and just start shifting. And we can see the 3 previous bits at all times. So we created something that's much richer, something that can move through time and have its own memory. And we can predict its behavior, like we can predict where the missile's going to go. So what we want to do is create circuits that have no inputs, that sit there and just draw pretty patterns in the LEDs. I'm going to show you a video now of a circuit done on an Arduino in the Arduino programming language with if commands that just draws pretty patterns on the LEDs. The next 10 circuits in the book are just playing with LEDs and making patterns in them. Here's how we think about them. They're just counting. They're counting state 1, state 2, state 3, state 4, state M. Now you could think of a really simple pattern with the LEDs. LED 1's on, all the rest are off. Then LED 2's on, and all the rest are off. Then LED 3's on, and all the rest are off. But we can make it more complicated. We can make state 1 have 2 LEDs on, and state 2 have the other pair of LEDs on, and state 3 have nothing on, and state 4, etc. Now there's some limitations to this circuit, and some limitations to the patterns of LEDs we can make. But pretty much you just can't repeat the same pattern with 2 states. In Chapter 7 we will be able to repeat the same pattern. So let's just browse through these. So here's the pattern of the LEDs. They're all off. One's on, this one's on, so it's just counting. And then by adding these AND gates, we can get the slowest step counting down to about 7 clicks of the blue circle moving through logicism. So play with the blue circle through logicism to see how we're reducing the flicker. Here's another variation. And here the outputs all change at once. The next 5 clicks, depending upon what state we're changing from, how many bits are changing, it could be 5 clicks. This is gating the input. So we've got a parallel load situation right here. Here we've got a 4-bit counter that counts up to 10. So when it gets to 1 plus 8 equals 9, so when it gets to the 8 and the 1 having a 9, then on the next clock pulse it resets to 0. So this counts up to 10. Download these circuits and play with them. Just figure out how they work. And here we're using a carry mechanism to change this from a counter that counts up to 16 to a counter that counts up to 256. And here we've got a pattern going. We're not really counting. So it's just scrolling these ones across one at a time. And here we've got a 1, and then it fills up with 1s, and then the zeros start coming back, and that's done by feeding the negative output of this last flip-flop back to our input. So these are the kinds of things that we can do with flip-flops that we can't even imagine doing with a Chapter 5 circuit. We just sit there and let it roll down the hill, like a car rolling down the hill. So here's where we stop. How do we design these things? I just showed you 10 circuits. You can look at a bunch of circuits at night. This is Don Lancaster's TTL cookbook, and it's basically something you read at night, and it has all, different patterns that engineers have come up with. I'm sure it's not all of them, but it's basically you look at what other people have done. How do we do something new ourselves? How do we do something new for the first time? How do we understand the process of designing these circuits and use it to extend into the world of more complicated circuits? That's the question. How does the brain work? An excitation table is best pictured by this diagram right here. If you looked at all the circuits we've built so far, we've had the flip-flops in a column right here on the right, and then we've had a bunch of AND and OR gates here on the left. And in the OR gates basically create signals or information that's fed into the flip-flops. So what's coming through here are J and K, or what's coming through here is D, or what's coming through here is T, or S and R. Let's go back real quick and look at one of those. Right here, you can see here are all ANDs and OR gates. And their sole goal is to create inputs here to the J and the Ks. And here are our flip-flops. So this is combinatory. So this is combinatory. And this is our logic, or our memory, that's clocked. So this is how we design circuits. We think about this model right here. Now sometimes it's drawn sideways like this, where the combinatory logic's on the bottom and the flip-flops are on the top and the output comes out the top. But you can see that there's another feedback loop going on. So what we're doing is we're beginning to take the feedback that created memory right here in the first place. We're taking that memory and we're feeding it back again, and now we're beginning to talk about how we design this process. So we're using this fundamental feedback in here, the guts of the flip-flops. Think back to how we build an SR flip-flop, and we're basically making our own custom flip-flop right here, our own custom module right here. So how do we begin? How do we begin talking about this? Well, what we want to do is build an excitation table, and that's what we're going to start off doing next. It's a lot like a truth table. This is what we were looking at in the first half of chapter 6. We were saying that an SR remembers. So we called this the remembering state. We called this the reset state. We called this the set state, and we called this the toggle state. We're not really going to deal with SR flip-flops. They are used just as a starting point to get the discussion going of the D and the JK and the T. The D flip-flops are so easy that the excitation table is easily created from the transition table, which we'll see in chapter 7. So because it's so easy, we're going to focus our attention down here on the J and the K and the T. So what we're doing is we're taking what was formerly one row right here. These two rows were one row in the previous slide. And this one row had Q here. So it was as if we had done a variable linear Carnot map. We'd taken these two rows and collapsed them into one row. We'd taken these two rows right here and collapsed them into one row, where the output was just 0. And we took the output of these two rows, which is 1, and then we took this one, which is the exact opposite of Q, and called it Q bar. This is the toggle row. So this was the remembering row, this was the reset row, this was the set row, and this was the toggling row. And we've done that for a specific purpose. You can see we did the same thing with the T flip-flop right here. So here's what we were looking at for the JK flip-flop. You can see that J, K, and Q become the inputs, and Q plus becomes the outputs. But this doesn't make any sense because Q is the output memory of the flip-flop. So this whole truth table really doesn't make a lot of sense. So what we have to do is we have to interpret it in terms of this diagram. Because what we're going to do is we're going to take the outputs of our current flip-flops and manipulate them with our chapter 5 combinatory logic circuits into creating new J's and K's for our flip-flops. So we're going to look at the output of our current memory and manipulate it into J and K's to set up our flip-flops. And then on the clock beat, so what causes this column Q plus to be evaluated is the clock. What causes J and K to be created, given a Q, is nothing. It's just continuously computed. There is no clock. It's combinatory. So when Q changes, J and K automatically change. But the clock doesn't look at them until the clock ticks. So these J and K's right here end up set up, and then they're looked at right here when the clock ticks, and that creates a new Q, and that Q comes around and comes back into here. So as soon as this Q plus is created, it becomes the current Q, and the J's and the K's get ready for the next clock tick. So this is all one big circle right here. Now what's interesting is we have this Q, we want to generate that Q. We have this Q, you want to generate this Q. We have this Q, you want to generate that Q. You have this Q, you want to generate that Q. And what we can see is that there's a pattern. It's easier to talk about than it is to discuss, but this is the pattern right here. This is how we take our Q's and generate our JK's. This is the design process. This is not a function of the circuit. So this is the Q we have, and we want to go to a current Q. So we could just go to a remembering, or we could go to what? A reset. So this row right here and this row right here, both will give us the same result. You can see that in both rows, J is a 0, but K can change its mind. So j is a 0 and k can be anything, any value. Same thing's true. So let's pick a row where we want to go from a 0 to a 1. Okay, here's a 0 to a 1. This is a set. Or what we could do is a toggle. If we can do a set or a toggle, then j is a 1 and k can be anything. Right? So from a 0 to a 1, j is a 1 and k can be anything. And the same thing's true over here, going from 1 to 0 to 1 to 1. This is the combinatory circuit right here. And then this is the clocked flip-flop circuit right here. And combining those two, we can create a design system for creating the combinatory circuit that feeds our flip-flops. So let's say we want to design this mod 6 counter, and it does sort of random things. Multiple bits are changing. From here to here, 2 bits are changing. From here to here, 2 bits are changing. 1 bit are changing, and then it starts over again. So this is our desired output of this circuit. We just want to turn it on, and it happens. Okay, so here's our desired output right here. Now what we want to do is we want to create a logical network. This is a combinatory network, so this blue box and this blue box are the same thing. You can see now the inputs are coming in on this side. They're not coming in on this side of the blue box, but these Q's, all these Q's and Q bars are what are coming in here. That's what's available to our combinatory circuit. And we want to design this so that when we hit the clock, you go from this row to 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 this row, and then start over again. This row to this row. So it's like counting. So I took this logical network and I moved it vertical. Here's what we want. We want to go from one row to the next. So we want to go from this row to this row. So we want to go, this row is right here, and then this row is our next row. And then when we get down to the bottom right here, we want to go to the start over again right there. So our present state is the outputs of the flip-flops. They become our inputs to our logical network. And then we want to design J1, K1, J2, K2, J3, K3, J1, K1, J2, K2, J3, K3. We want to choose a combinatory network for each of these that creates the necessary changes in these flip-flops on the next clock pulse. So when we hit the clock, we move from here to here. So we're zigzagging. We move from here, clock hits, we move from here, then here rapidly. Clock hits, we move from here, then to here rapidly. Clock hits, we move from here to here, and we move down to this row rapidly. So we're moving one row to the next. And then we get to this last row, we move up to here, right, and start over again. So the question is, what are these columns of J1, K2, K3? Okay, so what we do is we use this table right here. Q1 is changing to 0 to 0. So 0 to 0, J1 would be a 0, and K would be a dash. Q2 is changing from a 0 to a 1. So J2 would be a 1, and K2 would be a dash. So you can see here I filled out this table. Let's just randomly check something. Okay, we've got Q2 going from a 1 to a 0. So that could be a reset, or it could be a toggle. So it could be a reset would cause this change, or a toggle of a 1 to a 0 could cause this change. So a reset's a 0, 1, a toggle's a 1, 1, so J doesn't matter and K has to be a 1. So J doesn't matter and K has to be a 1. Okay, so I just randomly spot checked and it worked. And you can see the self-talk I'm going through. Okay, so this is our excitation table. And from this, we can build this logical circuit network. These are just outputs. J and K are outputs. J2, K2 are outputs of our network. Our inputs are our Qs. The Q pluses just momentarily exist. So they're going to disappear when we go to our truth tables. So here's our desired output. We can see that reflected here in our present state. Our next state drives us in a zigzag fashion when the clock ticks down to this row. So the Q plus state never really exists. But we think of it as existing inside the setup. So J1, K2, J2, these JKs set up this Q1, these next Qs. So when these are present in the wires here, these 6 wires in here, This arrow represents 6 wires in this particular circuit. They're going to cause this to happen when the clock hits. And then immediately when the clock hits, then this is going to be our output. So if we were at a 0, 0, then we're going to go to a 0, 1, 0. So I'm trying to put all the excitation table. This is the excitation table right here. Present state, next state, flip-flop inputs. This is the excitation table. But I'm trying to put it in the context of this drawing right here that shows the feedback loops. Okay, so all we're looking at then is a combinatory circuit like chapter 5, where we have our present state and we have 6 outputs. So we have 6 truth tables, 6 Carnot maps right here. We have 3 inputs for each of these that are available. And you can see that in only one case is there an AND gate, right here. All other times we could draw, in this 2x4 Carnot map, we could draw a party of 4, which results in no combinatory logic at all. Just one J1 is combining Q2 and Q3's outputs. That's it, to create that pattern. So we're taking our present state Q, feeding it in. These are the outputs of our current flip-flops. Feeding it into the circuits we're designing, and they're going to produce J1, K1, J2, K3 right here in this next state line. So these are the 6 wires containing these guys right here. So this is what the circuit looks like, and you can play with it. Here's the one AND gate combining the output of Q3 and Q2 to create this J. The one AND gate combining Q2 and Q3 to create that J1 right here. So this is our combinatory circuit right here. This whole block's right here. And these are our JKs, and this is our final output right here. Let's play with the circuit. Now we don't have to do this with a JK flip-flop. We can do it with a D flip-flop. We can do it with a T flip-flop. So here we're doing it with a D flip-flop. If Q1's a 0 and Q2's a 0, then our D has to be a 0. Q2's a 0 and the next Q's a 1. Then we want to change its value, so we make our D2 a 1. So you can see in all cases the D is a copy of the Q1, Q2, Q3 plus. But we still have to create a combinatory circuit for our D flip-flops. Instead of having 6 wires here, we just have 3. But you can see each one is a more complicated circuit. This is why JKs are often used. They result in a cheaper, faster, less energy, easier to troubleshoot circuit. The T's, yeah, you got to think about it a little bit. Okay, so here we don't want to toggle. Here we do want to toggle. Here we don't want to toggle. Here we don't want to toggle. Here we don't want to toggle. And here we do want to toggle. So that's why you think about it, building this. And then you can build, and sometimes the T flip-flop is simpler than a JK, most of the time it's not. So in a way, these counters that we've been playing with in this application section of chapter 6 have been self-correcting. So if we power on, and these flip-flops randomly power on, remembering randomly 1 right here and a 1 and a 0, then the clock hits, it's going to go to here, and it's just going to pick up and go around in a circle. But there's 2 states that aren't mentioned in here. 1, 0, 0. 1, 0, 0 doesn't exist. And 1, 1, 1 doesn't exist. They turn into these don't cares inside the truth table. So how do all these don't cares that we've chosen to be ones here and here and here, 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 how do those ones that we've chosen to be, these don't cares that we've chosen to be 1, how do they influence what happens when we power on to one of these states? What happens if we build it out of D's or T's or SR flip-flops? How does that change what happens? If they power on to 1, 0, 0, what could happen? It just go to itself over and over and over again. never get into this loop right here. Presentation to the engineering seminar one year was a fellow who designed circuits for torpedoes. And the torpedo, if you know, is pushed out of a submarine by compressed air. And then once it gets away from the sub, it's supposed to power on, find the sub, and drive itself away from the sub. If it doesn't power on, the sub could hit it. If it powers on in the wrong state, it could turn around and come back and hit the sub. So when that torpedo powers on, the initial state's very, very important. And this particular torpedo, the engineers hadn't done this analysis to figure out what happens when these unused states are powered into, when the circuit powers on. And they didn't correct for it, and about 1 out of every 1,000 times, it would power on to the wrong state. And during testing, they never checked, they never discovered this. And the company that built the circuit did extensive testing. It was the Army's engineers that did more detailed testing, because they don't want to lose a sub, that found the problem. So let's call this the submarine problem. So how do we deal with it? Well, this leads into the next big design mechanism that we need to go through. This is actually what happens. If you get the circuit up and play with it, you'll see that if you power on to 111, it'll jump back into the loop here and go on around. And if you power on to 100, it'll jump back into the loop here and power on. You know, and so it'll recover from powering on to the wrong state. But this is an interesting question. And right now, all we can do to test it is to build the circuit. We'd like to have some kind of mechanism that shows up inside of our design process that points this out when it's a problem. You're going to have 2 homework problems on this, so get ready.